So I have a lesson here, counting problems that involve geometry. Always found these problems to be challenging, at least partially because no two of them seem to be the same very often, at least. So let's take a look at a few of these interesting problems. The first one, how many line segments have both their endpoints at the vertices of a given cube?
Twelve.
12 line. So you're counting edges.
That's not it though.
What other kinds of segments can have their endpoints at a pair of vertices of a given cube?
Face diagonals, space diagonals.
Yeah, we've got the diagonals to count too.
28. You just choose any two of them and connect them.
Yeah. So we could have said edges, face diagonals, and space diagonals, and counted those like casework. And it turns out there are 12 and then 2 face diagonals per face. So that's 12 more, and then 4 face diagonals. However, we can remind ourselves, hey, there is 1 segment for every 2 endpoints. So really, we're just counting the pairs of endpoints because we have a 1-to-1 correspondence that allows us to more easily count. So 8 times 7 over 2 times 1. And that gives us 28 much more easily. So it's very often good to say, okay, what is it that we're counting, or is there some other description so that we can count something more easily using a 1-to-1 correspondence? Okay, let's take a look at some more of these. So what are we doing here to count the ping pong balls?
Oh, 5 squared plus 4 squared plus 3 squared plus 2 squared plus 1 squared.
Okay. What does that equal to?
55. Oh, it's 5 times 11.
So you said 55. Did you just add them up and then you started to compute in a different way?
I remember there was like this weird formula thing. I just remembered. It was like n times n plus 1 times 2n plus 1 divided by 2.
You're
Something
close.
like that.
You're close. Let's say that we wanted the sum of the first n squares, positive squares.
N times n plus 1 times n 2n plus 1 divided by 6.
Divided by 6. Have you ever derived that formula?
No.
Do you know how you might go about it?
I've tried, but I don't think I could do it.
Yeah, this is challenging. You know, let's take an aside. Let's try to do that. So let's see. Let's do a simpler version first. Let's talk about, well, have you ever noticed that the sum of the odd integers turns out to be just real nice and easy as a formula?
Square.
Why is that true?
I don't know.
Well, how much practice do you have with summation notation?
I've had some practice. I'm okay with it.
Well, first, let's see. How do we know this is n squared? Well, 2n minus 1. What could we say about each of these odd numbers as they relate to squares?
1 is a square, 3 is 1 less, 5 is 1 more, 7 is 2 less, 11 is 2, 9 is a square, 11 is 2 more than a square.
Perhaps. Let's take a look at partial sums. 1 is 1 squared. 1 plus 3 is 2 squared. 1 plus 3 plus 5 is 3 squared. What if I asked you, what is 7? Could you use what we're writing here to get another perspective on 7?
Uh, Seven is 8 less than 4 squared. Wait, no, 9 less than 4 squared. And then 1, 3, and 5 add up to 9.
Okay, you're moving in the right direction. What's another way you could say that?
The sum of the previous odd numbers plus 7 is 16.
True. You're almost there. What if I said I wanted you to isolate 7?
7 equals 4 squared minus 9.
Yeah, 7 is the difference between 4 squared and 3 squared. And if we wanted, we could see that as a difference of squares. It's not necessary for our purposes. I just wanted to point out each one of these odd numbers is the difference between a pair of consecutive squares. 1 is 1 squared minus 0 squared. 3 is 2 squared minus 1 squared. 5 is 3 squared minus 2 squared, and so on and so on. So if I wanted the sum 1 plus 3 plus 5 plus 7, all the way up to the nth positive odd integer, how could I rewrite that?
It's equal to n minus 3 plus, n squared minus 2n minus A equals 2n minus all of the other ones, except for 2n minus 1.
Let's start by rewriting 1. Now let's rewrite 3. Sometimes it's good just to write things in a different way. Even if we don't know where it's going, we might do it for a particular purpose. We might know where it's going, but sometimes it's good to play until we understand where it's going.
Oh, they cancel out.
What cancel out?
Okay, so it's 1 squared minus 0 squared, 2 squared minus 1 squared, and the 1 squared and cancels out. So it's just 2 squared plus 3 minus 2 squared cancels out the 2 squares and just leaves it with the 3 squared on and on. Dot,
Now,
dot.
what do we call this?
Not sure.
Have you ever heard the term telescoping series?
Oh, telescoping, yeah.
Yeah, that's what we're doing right here. Every term except the 0 squared and the n squared cancels out with a corresponding term. So all we're left with is n squared minus 0 squared, which is, of course, just n squared. So in order to come up with a closed form expression for the sum of the first n positive integers, of the first n positive odd integers, we came up with a way to rewrite each one that telescoped. So what if we just wanted the sum of the first n positive integers?
N times n plus 1 divided by 2.
How do you know that formula works?
I don't know. I just remember it.
There are different ways to derive it. Well, we know that this sum right here now is n squared. Is there another way that we can rewrite the left-hand side, the summation?
Wait, if it's starting from 1, it's just the number of, it's just n times the middle number, which is n plus 1 divided by 2. So it's just n times n plus 1 divided by 2.
We could use that Gaussian summation, but I want us to go in a different direction that relates to what we're doing today. So I just wrote out all the terms from the summation above, right?
Mm-hmm.
How could you regroup that?
Group the first 2 and then the second 2. Oh, you group the first 2 together since it's 2 minus 1 plus 2 plus 4 minus 1. Then the minus 1s cancel out with the 2. So it's just 2 times 2 left.
All those terms are alike. How are they alike?
They're all 2s. 2 times an integer.
They're all multiples of 2.
So that makes them odd.
Well, let's ignore the minus 1s for now. We have all these multiples of 2. How could we rewrite them?
2 times 0 plus 1. 2 times 1 plus 1.
Oh, I'm thinking simpler than that.
Oh. Just add those all up.
Here's what I'm doing. I'm continuing to use n terms at a time so that I can rewrite this in terms of simpler summations. And now look at this and compare it to the original summation.
That's the same thing, right?
It is the same thing. Did you know that we could do that with summations?
Yeah.
Yeah.
So 2 into the 2k, and minus 1, you just put the parentheses around that.
Yeah, if we ever have a summation with two pieces, we can break it up into two different summations. I'm leaving off the indices there, but you see the idea. And it doesn't really matter what A and B are, they can be functions. Or if we have the summation of a scalar, let's just say a constant times A, we can pull that constant out. And put these together, if we have a constant times A and a constant times B, and A and B might be related to the index variable K, if we use an index variable like that. But so long as M and N are constants, we can pull them out like that and set ourselves up with simpler, more organized summations if we want. But back to where we were. What we know is the two summations that are underlined in red, these are the same, right? Sum of the positive odd integers up to n, and 2 times the sum of the positive integers up to n minus the sum of a bunch of ones. Well, since those are the same, this one also equals n squared. Do you see that?
Mm-hmm. Wow.
Oops, a little too far. Okay, so on the left-hand side of this newest equation, we have 2 times the sum of the first n positive integers minus, wait, what is that? The sum of n ones.
1?
No? The sum of n ones.
N?
Right, right. Good. Your mind is struggling through this new notation.
Yeah.
Obviously, that's an easy question, but it takes a little while to get used to the new notation. But as you get used to it, you're going to be able to use it more and more creatively. It's going to seem like the simpler thing to do once you get a hold of it. So now this is equal to n squared. What can we do now?
Simplify to the 2k part thing.
What do you mean simplify?
Uh,
It seems pretty simple. The sum of the first n positive integers, well, times 2. What does that equal to?
k times k plus 1 divided by 2.
Not k times k plus 1. K is our index variable.
Oh, n times n plus 1.
Yeah. K is only being used within the summation. And I remember when I was first doing summations, I would often get the index variable confused with the other variable that I was using. It takes a little while to get used to it.
Never used it that much. Sometimes I've seen it, but not really. It's weird.
Once in a while, I still get them confused, just writing too quickly. And you know what we've now done?
Times 2. Oh.
We derived the formula for the sum of the first n positive integers or the nth triangular number, either one. Let's take a look back at what we did, and let's ask ourselves if we can use this method to come up with a sum of squares. Where this started was taking a look at each odd number and saying, oh, look, I can write this as a difference between a very simple square differences of squares. So it's kind of like reaching for a polynomial of one higher degree. So if we wanted a sum of squares, and what we did is we eventually got this equation, right? Like this equation was, this is what we were after. So if we got a sum of odd integers from differences of squares, which telescoped, what could we try next?
Try to do the same thing with squares?
Do you know what squares are differences of?
Other squares? No.
Yeah, that's hard for me. I'd have to think about it for a moment to come up with an answer. I can come up with an answer, but it's not as easy. What's easier? Let's say that the hardest part is creating the telescoping series. That's hard to engineer, so we want to make it as easy on ourselves as possible. What's sort of a level up from differences of consecutive squares?
What is the difference of squares? Is there like a number, type of number?
What was that question?
Is there like two kinds of numbers that have a difference of a square or something?
Like I said, that's a hard question for me to even answer. I would have to engineer it, but we're going to see how it's engineered. Let's work on creating a telescoping series, right? Now, we have a telescoping series here where the difference between the general term gives us a general odd number, or a general number of degree 1 less, right? Because you can look at n squared minus n minus 1 quantity squared and know that the n squared terms are going to cancel. You know, even before you write it out, even before you expand n minus 1 squared, you know that much about binomials. What is something that we could do that is a level higher? Right, in our example here, we have n, just a sum of n. It's embedded within 2n minus 1, but later we were able to strip away the 2 and the 1. And then we were able to derive the sum of the terms that were in, or more generally in. Okay, I'm going to give this piece to you. Let's examine differences between consecutive cubes. And let's just see what we get.
primes, except for one.
We do get a whole lot of primes in this series.
Uh,
91 is not prime, however.
yeah.
What's n cubed minus n minus 1 cubed?
Um, three n squared minus 3n plus 1.
Good, I agree. Okay. Now look at the left-hand sides of all these equations.
They follow the pattern.
They follow that pattern. What happens if we add them all together?
Yes. 1 squared minus 3 minus multiples of 6. Wait.
There is a relationship to multiples of 6 in this pattern. In fact, each difference of cubes is 6 times a triangular number plus 1, which is kind of cool to notice.
Whoa. That's weird. That's a weird thing to know. Does that help us though?
It's a little bit weird. It's not going to help us with this problem, but really it's just saying, hey, we have 6 times n minus 1 times n over 2 plus 1.
Oh.
So 6 times the n minus first triangular number plus 1. I've made that observation handy once or twice. But let's take a look in the green. That series. In the gray to the upper right, I've got examples of that. What happens in each case when we add those weird terms together?
They cancel?
What do you mean by that?
The terms cancel somehow?
Somehow?
I don't know.
Let's go back to our previous example. When we had the sums of the differences between consecutive squares, what happened?
Some of the terms canceled. Just left us with 1 square.
Just left us with n squared minus 0 squared. What are we going to be left with here?
N cubed.
Everything cancels out except minus 0 cubed plus n cubed, or we can just say simply n cubed. So now let's rewrite what it is this means. Because our general term is 3k squared minus 3k plus 1. And I'm saying k because I want to use that as an index variable. The summation, as k goes from 1 to n, is 3k squared minus 3k plus 1. Every one of these terms can be written that way for some k going from 1 to n. And all that is equal to n cubed. Now, a few moments ago, and I guess maybe you'd seen this a little bit before, we reminded ourselves that we can break a summation into pieces. So what I would like for you to do is to tell me how we can break up that summation into pieces.
I don't know. This is hard. I don't know how to do that. I don't know.
Let's take a look back. In the gray on the right-hand side, we can break summations up into pieces and sum each piece. And we could see that down here. You know, if we write them out term by term without computing, just write out 2 times the index variable minus 1. We can separate the index variable from the 1. We can take out the factor of 2. We can break summations into pieces, and we can factor.
Could that help us down there? I feel like it could.
It's worth finding out.
You just split them up into 3 parts.
Okay, what are our 3 parts?
3k squared minus 3k plus 1 each part.
Okay, I'll go ahead and tell you, I agree, but we can do even more. Now what can we do? We can break a summation into pieces. What is the other thing that we said that we can do?
The n part is just n. The one part is just n.
That's true. We'll come to that. But there's something else that we can do first.
You could pull out the -1 into 3k and subtract the overall thing.
That's true, but we can do even more.
Pull out the -3 completely.
Yes, and what can we do with the first term?
You could pull out the 3 too.
Yeah. What is that right there? Like, say that out loud. This is 3 times what?
What are the sum of squares?
Oh, you just said it. It's 3 times the sum of the first n positive squares. And then minus 3 times what?
The nk part is just n times n plus 1 divided by 2 times 3.
I'm sorry, say again.
Wait, the minus 3 nk is 3 times n plus 1 divided by 2.
Okay, right. That's the sum of the first n positive integers, and you already have a formula for that. So let's rewrite this equation now, because you have a formula for almost every piece of this except the piece that we want. We previously derived that. Now we can isolate and find a formula for the sum of the first n positive squares. Oops, I miswrote that. There we go. So 3 times the sum of the first n positive squares equals n cubed plus 3 times n plus 1 over 2 minus n. So let's work on that right-hand side.
That seems weird. Okay.
Seems weird. The toughest part is the fraction. So let's give ourselves a common denominator. A lot of times if you say what is challenging out loud, you realize it's not as challenging as you think, or you can find a way to handle it.
Oh, you pull out the n. You can pull out n for all of them.
We can. I was going to handle that factoring at the end. Check my work. The older I get, the worse I am at working while I talk.
Ooh.
And you can tell me if we're in agreement.
Okay. I'm so far there.
Okay, so far so good.
Yep.
Well, there we are. We have one final step, and what is that?
Divide both sides by 3.
Divide both sides by 3.
That should do the trick.
And now, if we want, we can factor the numerator. How much does the numerator factor?
Well, that's weirdish.
Yeah, and this one's it's harder to remember, but what is a nice way to remember that weird factor in the numerator, that 2n plus 1?
I just remember the value for 5 squared, and I just kind of test it sometimes.
I used to do that too, test multiple versions if I remember the formula imperfectly. But for this one right here, one thing that I did was I just recognized that 2n plus 1 was equal to n times n plus 1, which are the other two factors. That made life a little bit easier for me. Okay. Wow. So much exploration that we can do just from asking how we can generalize one math counts problem. Not even one of the hard ones either, right?
Yeah.
Okay. Actually, before we move on, I want you to say in your own words, how did we get here? Generalize the ideas behind this.
It's a long way. Some subtraction and then playing with the numbers.
What we did was we viewed a sequence, we viewed a series of differences, right? We created an easy to sum telescoping series. And the differences of cubes turn out to involve squares and stuff below that, right? The differences of consecutive powers, in any power, any degree polynomial that you take, if you take the difference between the nth value and the n minus first, like f of n minus f of n minus 1, where f of n is some polynomial, you will get a polynomial of degree 1 less than you had before. And if you do it simply enough, like just into some power, you could do this if you wanted with n to the 4th minus n minus 1 to the 4th. And if you do, you're going to end up with something with n to the 3rd power. What would that allow you to do?
Kind of like telescope it out, like work on small parts.
Okay,
To
what's going to be in those small parts?
all the numbers until the end.
Well, the small parts, when we did differences of cubes, the small parts were a sum of squares, a sum of integers, a sum of things to the 0th power, and that allowed us to derive a formula for the sum of squares. What could we do with the differences between 4th powers? Would that allow us to derive anything new?
Maybe.
If it did, what would it be?
Don't know.
Do that subtraction right there. What's n to the 4th minus n minus 1 to the 4th? Do that subtraction and then think about the summations of the terms.
They still cancel?
What do you mean?
The ones cancel and then the twos and then the threes, ...
What's n minus 1 to the 4th power?
Fourth power is kind of weird. Into the 4th minus 4n squared, n cubed, plus 6n squared, minus 4n squared.
Minus 4n squared. You already have a 6n squared term.
Oh, 4n, just 4n.
Yeah.
Plus 1.
Good. Okay, so differences between 4th powers give you 3rd powers, 2nd powers, 1st powers, and 0 powers. And if you make a summation out of those, well, you already have a formula for everything after the cubes. What does that mean that you're going to get?
The sum of cubes?
A sum of cubes formula.
It's always one less, right?
Exactly. Exactly. So we can always create the next higher power formula if we need it. So I'm going to leave this for you as an exploration. See if you can do this between now and the next time we work, okay? Come up with a sum of cubes formula. Don't worry, I will save all our work today into your Dropbox.
Okay.
Okay, let's take a look at number 2.
That was weird.
7 points are marked on the circumference of a circle. How many different chords can be drawn by connecting 2 of these 7 points?
7 choose 2, 21.
Okay.
That's simple.
Yeah, and a lot of times if we're counting something geometric, we can count it according to some geometric, some describable parts of it. And that's what we're doing in the first, well, the example problem and problem number 2. That'll become a little bit more complicated and harder problems, but we'll see that later. Okay, the usual coloring pattern on an 8x8 checkerboard is changed so that 20 unit squares are now colored red and the rest are colored white. When the board is folded in half along a parallel line to one edge of the board, exactly 7 pairs of red squares coincide. Compute the number of pairs of white unit squares that coincide.
Wait, how come only 7? Because there are 20 colored red. I feel like this is weird.
So we have 8 times 8, 64 squares.
Oh. 19.
Let's get 19.
Since only seven pairs of them touch each other, there's still 6. Wait, yeah, 6 of them that touch white squares, and then there are 44 total white squares minus 6 equals 38 of them that touch white, and then divided by 2 number of pairs.
So what was your answer? Did you say 19? What did you say your answer was?
19.
19. Okay, good. I get that too. Okay, nicely done. You grouped things into different types of pairs: red pairs, red-white pairs, and white pairs, and counted according to those groupings. Okay, moving on. We have a 4x4 grid. Each point is 1 unit from its nearest horizontal and vertical neighbors. What is the greatest number of segments that can be drawn using pairs of these points as endpoints such that no 2 segments are the same length? Okay. So we're counting the number of possible segment lengths. Okay.
There's a lot. There are a lot.
There are definitely at least a few.
Should we just count the side lengths?
How do you mean?
Like this, okay, so we'd have like 2 points. They should make like a right triangle, and we measure the side lengths and how many of those.
Okay, so we can think in terms of right triangles. I like that idea. Like if we want the length of that segment.
It's 2, 1.
Okay, oh, right. So we are counting the number of ways that we can form a right triangle and get some different length than any we have counted up before.
Eight.
I think you're very close. Let's try to lay this out carefully. Really, we're trying to count the number of ways that we can find a squared plus b squared. But what can a and b be? What are the possible values of a and b?
A could be 1 through 3, and B could be 1 through 3 too.
Is that true?
Right. But then you have to divide the total number divided by 2, since you counted some of them twice, basically.
We would count some of them twice, but not all of them. 9 divided by 2 doesn't count anything.
Oh, then it's 5. Because the big one, you don't have to divide it by 2. There's only one way.
What I'm going to say, slow down. These counting problems that involve geometry are harder. You need to be precise in order to get this right.
Okay.
First of all, 1 to 3 is not the correct range.
4?
Can you make a horizontal or vertical distance of 4?
No, I think. Not sure.
Now, you were correct before. 3 is the obvious limit
Yeah.
of horizontal or vertical movement. We can move no more than 3 units from one of these dots to another in either of those dimensions.
Uh, 6 ways, because if you have 1, you have 1, 2, 3. You have 2, you don't count the 1, you just count 2, 3. And then for 3, you just count the 3. So that's one way.
This is not yet the correct answer. Clear your mind and look back at the geo board.
Oh, we forgot the straight lines. So there are 3 more. Or 1, 2, 3 lines.
There are 3 more. How could you have described this correctly all at once? Could you have given, a lot of students who solve this problem are probably just going to get there by playing around. But of course, what we'd like to do is elevate our ability to use, better organization. You noticed the symmetry. So I might say something like, hey, let's let A be less than or equal to B. And A is at least 0.
Oh, 0, 1, 2, 3.
3. But we have to exclude 0, 0.
0, 0 is just the dot.
Mm-hmm. And now what we're really doing is saying, hey, we want to pick two numbers from a group of 4, but we've ordered them. So we have 4 squared ways to pick 2 out of, pick 2 values from 4. Subtract off the ones where they're the same, divide by 2, add back the ones where they're the same, and then subtract 1 because 0, 0 is disallowed. And we get 9 as the answer. This right here, this is tough until you've built up some experience. But as you build up some experience and you simplify the way that you're approaching the problem, simplify it a little further, simplify it a little further, that will become the natural approach or something like it. It's one possible way to go about it, at least. Okay, well, that was a pretty good amount of exploration for 5 problems.
Yeah.
And I'll go ahead and tell you this about the sum of cubes. You may be able to guess a formula if you write out a few. It's an interesting formula and it's surprising. It's actually, in some sense, more recognizable than the formula for the sum of squares.
Okay.
All right. Any thoughts before we wrap things up?
It's just a square. The sum of cubes.
We'll see. We'll see.
Because 2 cubed plus 1 cubed equals 3 squared. And then 1 squared plus 2 squared plus 3 cubed equals 4 squared.
Careful.
Wait.
What's 1 cubed plus 2 cubed plus 3 cubed?
Oh no, 6. It's the sum of the 1 plus 2 plus 3 squared.
Now see if you can justify that.
Yeah. N times n plus 1 divided by 2 squared.
Nice work. Now see if you can derive it. See if you can prove that that works.
Okay. That's gonna be hard.
You can do it. You've got all the tools, and you've
Okay.
already found a way to generate the formula, so you have something to check it against.
Okay.
Next time.
Thank you.
Welcome.
Bye.